Deductive reasoning demands absolute, guaranteed perfection. If the starting premises are true, the conclusion is locked in stone. Within this rigid system, error is impossible. Provided the starting facts are accurate, the conclusion is an inescapable certainty. But step into a courtroom, a laboratory, or an intelligence briefing, and that absolute certainty vanishes. Analysts in these fields rarely work with premises that offer a 100% mathematically guaranteed outcome. They operate in the gray area of conditional probability, evaluating claims based on evidence that remains incomplete. Navigating real-world ambiguity requires analysts to move past binary truth and adopt a rigorous mathematical approach to uncertainty. This scale shows the core metric replacing deductive validity, inductive force. It reaches this threshold when the conditional probability is strictly greater than 1/2. But it has an upper boundary. Probability must stay below 1, or it becomes a deductive certainty. Practically, this means that given the provided premises, the conclusion is more likely to be true than false. Arguments resting exactly at the 50% mark completely lack inductive force, as they offer no reason to prefer the conclusion over its opposite. Crucially, inductive force measures the logical relationship between premises and conclusion, regardless of whether the premises are currently verified as true. Inductive force mathematically verifies whether a specific conclusion represents the most rational expectation based on the information provided. Once we establish that probability must exceed 1/2, we must determine how to calculate that figure in complex scenarios. Proportion is our most common analytical instinct. We see it clearly in a simple draw for an ace. Proportion works within closed systems. In a standard 52-card deck, the presence of 4 aces creates a fixed probability of 1 in 13. Frequency offers a different statistical tool, relying instead on historical patterns over time. If historical records show London snow in 14 of the last 100 Decembers, we can project a 14% probability for the coming year. However, proportion and frequency often fail in human scenarios where data is non-existent. A first-time political candidate, for example, has a historical win frequency of 0. These situations require a different logical standard, the degree of rational expectation. Rational expectation measures the degree to which an agent is entitled to believe a proposition based on qualitative, non-numerical evidence. In logical reasoning, probability serves as an epistemological stance, quantifying exactly what the current evidence entitles us to believe. Consider an everyday argument. Fiona lives in Inverness, Scotland. Therefore, Fiona owns at least one wool garment. This argument contains a structural gap. Residence in a cold city alone fails to push the probability of the conclusion past the required 50% mark. An unstated premise, the fact that almost everyone in Inverness owns wool, completes the logic and provides inductive force. Analysts must uncover these implicit quantifiers, like almost all or most, which hide beneath the surface of conversational language. This brings us to conversational implicature, where our common use of the word probably differs from its logical definition. While most people expect a probability of 80 or 90% when they hear probably, in strict logic, the term applies to any value over 1/2. These structural evaluations lead to the standard of inductive soundness. An inductively sound argument must be both inductively forceful and built upon premises that are verifiably true. Even so, a perfectly sound inductive argument carries a persistent risk. The conclusion can still, on occasion, be false. Analysts build inductive force by using a mechanic known as inductive inference. Inductive inference involves taking known data from a sample and extrapolating it to a larger population. If every goldfish you've ever fed cat food has died, this sample projects a clear probability that a new goldfish will suffer the same fate. This works because the biological sample is relevantly similar to the broader population of goldfish. Contrast this with an observer in the Arctic who sees several white bears and infers that all bears globally are white. Formally, this bears the same structure as the goldfish argument. Practically, it results in a false conclusion. Evolutionary biology reveals the flaw. White fur is a specific adaptation to snowy climates, meaning the Arctic sample does not represent bears in other environments. Extrapolation only creates inductive force when the sample is representative, meaning it is relevantly similar to the total population being studied. An analyst can build a formally forceful argument on paper that is easily defeated if they fail to verify this qualitative representativity. Real-world analysis often moves beyond single sample extrapolations to look at complex webs of evidence, as seen in the trial of Dr. X. The case rests on 4 premises: medical knowledge, opportunity, a strong motive, and incriminating witness testimony. Isolated facts are insufficient to prove guilt beyond a 50% probability. Thousands possess medical knowledge. Opportunity alone doesn't confirm a crime. Individually, these fail the inductive force test. Force is achieved through evidence convergence. Conjoining these independent probabilities creates a much stronger logical expectation. Effective inductive reasoning relies on this compounding power, where independent streams of evidence converge to support a single conclusion. Navigating the world requires us to move beyond the search for binary certainty and embrace the calculation of conditional probability. Mastery lies in identifying implicit premises, verifying that samples are representative, and understanding how independent facts converge. Mastering inductive logic transforms raw probability into a structured expectation, allowing analysts to navigate evidence with mathematical precision.